before we can start any experiment or any on certain subjects, we have to know exactly the objective first. Okay, the objective, and we have to know some of the basics ideas. Okay, some of the basic ideas or the basic knowledge regarding the subject that we want to study. So that is the first one. We have to do some study first so that we can really realize what is the main problem of certain what we call it subject. Okay, and maybe we want to study about the problem in food manufacturing. Okay, so we have to know, we have to learn about the manufacturing process of foods, the type of foods, the ingredients, and all. So we also need to know the process involved in producing the, let's see, the foods, or any processes involving uh, from the first process to the end of the process until the finished product. So then we have to select the factors, and we also have to determine the ranges that we want to study, and we have to look all of the factors that could give effect on the output. So however, at the first stage, it is advisable, okay, it is recommended for you, for us, to just look on minimum number of the levels, okay, the minimum number of levels, and also the minimum number of the factors. So we have to do some preliminary study to compare what we have obtained, the knowledge that we have obtained from reading, from survey, or from any source of information is reliable. So then select the response, okay, selection of responses. So we have the input, we have the factors, and then we have to know what are the most important output that we want to collect. So most often the average of standard deviation of the measured accuracy will be the response variable. So to get the standard deviation, we need to have an amount, okay, some amount of data. We have to collect it, and the data could be from one, two, or more uh, response that we can get from several types of factors. So the next one is to choose the experimental design. Okay, decide the factorial fraction experiments, select the replicate sample size, run order for the experimental trial, and decide whether or not blocking or other randomization methods are involved. In conducting experiments, uh, it is recommended for us to perform the experiment in random, not in sequence, so that we can eliminate any bias judgment or any bias measurement data. Uh, the sample size of the experiment also we have to choose it, and we have to calculate depend on the number of factors, the number of level. So then after that only we can perform our experiments. So after we collect the data, we have to do some data analysis. Data analysis, the explanation is written in this slides. If you read all of the contents in these slides, and also the second slide of chapter 6, you know how to carry out analysis of certain data. And from the analysis, from the calculation also, there are some examples showing how can we do the conclusion or any recommendation for further study. For example, uh, so in experimentation, in experiment, it is important for us to understand that we can create new hypotheses based on the previous uh, literature study. Okay, from reading, from journal, we can create hypotheses, and from that hypothesis, we can create our new experiments. So from new experiment, we collect the data. We also can create another new hypothesis based on the calculations that we do according to the methods explained in statistical books or any calculation method in this course. And don't design a single large compressive experiment at the start of the study. We have to start preliminary study. We have to start it with small experiment as we confirm that the factors, the levels is applicable, then we can run the whole experiment. So by doing that, we can save our time and also cost, okay, for our experiment. So in our chapter, in this subject, so the calculations involved in chapter 6, we have designing engineering experiment, as what I already explained, and then we also have the randomized design single factor experiment, analysis of variance and multiple comparison using ANOVA, and also we have the residual study. So today I already uploaded another chapter, another slides for this chapter. So if you see on the slide, the second slide, you can see some of the benefits, objective, how to conduct experiment, the method, how we can conduct the experiment, and also the sequence of doing the experiment, to design the experiment, and also in the experiment, what are those things that we have to do. Okay, in the experiment we have hypothesis, and from the hypothesis we can have our objective, and then we can conduct our experiment, perform analysis, and then we have a conclusion which might lead to another hypothesis, and then the next explanations or the next contents in second slide of chapter 6 is quite similar to the first slide provided previously. So to this slide, okay, this is the first slide. We have explanation on how we are using the ANOVA. So you can read both of it. I suggest you read both of it so that some of you might think that the second slide is much more easy to understand, but maybe some of you also have opinion that the first slide is much more easy to understand. So let's continue with the multiple combustion techniques. This technique is used to test on individual level means. Okay, so from the previous study, we already studied about the F table. Okay, and in ANOVA, we are also looking on the F value of the F. We call it a single parameter F in this subchapter. And from the F, it tell us whether a factor has effect on the response or not. So it already explained in chapter 5, I think. But there is one weakness in ANOVA, whereby ANOVA cannot decide the direction of the influence on factor. It can only mention, or it only can state, or to show us, it only able to show us how big or how certain factors give influence on the results, but it's not showing the direction of the influence. In the previous, maybe chapter 4, I can't remember, if I'm not mistaken, in chapter 4, you already learned on how to do the box plots. So this is methods that we use to show the vector, okay, the vectors or the relation between certain vectors or certain level to the output or to the results. So we can use the box plots to show it, or maybe you can use another graph, type of graph, to show the magnitude or the tendency of certain vector. So in the box plot, the plot indicates the changing and hardwood concentration. Hardwood concentration has a strong effect on the paper strength, especially higher hardwood concentration produces higher observed paper strength. So we can see that we increase the hardwood concentration, the tensile strength also will increase. So this what we say, or what we means by the magnitude or the directions. So box plots show the variability of the observation within the factor level and the variability between factors level. Okay, so we have a here is a vector, and we also have the level, and it already shown the relation in one level and also relation between different level. Okay. However, less subjective approach is required to test the individual level means. Then we have the multiple combination procedure. This technique is used to make comparison between two or more levels. Subsequent to the analysis of variance. When we run an analysis, we have the variance, we can calculate the variance, and then we can calculate the F0 value. Okay, F0 value, and then also we can have the F value from the table. We can make comparison between F0 and F table, or we can say as F test. And for comparison, we need to have the hypothesis. We need to have the null hypothesis and the alternative hypothesis. So this here showing the alternative hypothesis. There is a condition where the mean of one factors is always not the same. Okay, it's always not this, but there are also the possibility that certain means value that we can get from certain level is not equal, but in another case there are some level which have the same means. So multiple comparison learning allow us to investigate hypotheses that involve mean of individual level. For example, we might have interested in whether mu1 is different from mu2, or mu2 is different from mu3, and so on. Or maybe we can have the mu1 to mu2 is equal or not. So we can do comparison between mu1, mu2, mu3, mu4, and mu5. One of the major problems with making comparison among level means that unrestricted use of this comparison can lead to an excessively high possibility of type 1 error. For example, if we have 10 level, it means in which the complete null hypothesis is true within alpha 0.05. We have to do calculation, or we have to do analysis on amount of data by repeating calculations, comparing between the null hypothesis and alternative hypothesis. If we have 10 level or 10 factors to compare, then we have to conduct long or time-consuming calculations. Series test t-test between all pair of level means will make a possibility of making at least one type error very high. So we are going to have a type 1 error most of the cases. Another thing is the possibility of making at least one type 1 error increases as we increase the number of independent tests T. Independent t-tests we make between pairs of level means. And then we can use the least significant difference LSD test to test the difference between the individual level means. The basic requirement of the test is F0 for overall analysis of the variance ANOVA must be significant. If F0 was not significant, no comparison between levels are allowed. Okay. So in the previous chapter, there is a judgment method that we can use to determine whether the F0 is significant or not. Okay. So because of the data in experiment, in statistic we assume the data is taken randomly, and we could have bell curve distributions. This graph here is representing the t distributions. The height of the graph here, the maximum height of the graph, it depends on the degree of freedom. Okay, when t 30 degree of freedom, it is a 3 distribution with the OF of the t. What we call it as infinity. Then we have the much more value here. This is a normal standard distribution when mu is 0 and the standard deviation is 1. Okay, this is the most, we call it a perfect bell curve distribution. And when the number of sample or number of data is too large, we can assume as infinity and Vxs. And the equation that we can use to do tests between a level, we can conduct the t-test, okay, comparing between the I and j level. Okay, maybe we have first level, second level, or maybe we can compare between the first and the third level, or first to the fourth level. So it depends. I and j is representing the level number. So if you have the hypothesis h1, if I is 1, j is 3, then we have the h0 mu1 equal to mu3. h1 is mu1 not equal to mu3. So comparing between this level, we can use the t-test. And this is the formula here. And the n, small n here is the response number. If we have a 6 data for each level, so that means the n is 6. And we have to calculate the MSE as we calculate it in the previous chapter. We can you can do how we can calculate the MSE, and you have to you can compare it. And the value of MSE, we can obtain it from the overall ANOVA. The DOF of T is equal to DOF of MSE. So the degree of freedom, we have to look back on the calculation degree of freedom, so we can have the T value to compare. So after that, we can use the two-tailed test for T for specific level of type 1 error alpha. So this is not equal to, so that means we have to do the two-tailed test. So actually, in any situation, if the alpha value is not provided, you just can go for the alpha 0.05. So in your group reports also, you can just select alpha 0.05 to do your analysis. If there is no requirement to use any other value of alpha. So then we have the alpha, we have the number, and we have the degree of freedom. Then we can see we can get the T from the, this is the maximum, the example of the table. When we conduct two-tailed test, that means alpha I divided by 2, as I explained before in the previous class. So you have to look on the alpha divided by 2. Okay? And you have to make conclusion. If the t value determined by equation fall within the limits, we cannot reject the null hypothesis. Okay, if the t value falls beyond the limits, is larger than the plus t value, or it's smaller from the minus t value, then we can reject the null hypothesis, saying that there is difference between mu1 and mu3, or mu1 and mu5, or whatever level that we compare. So using the same data to show you the calculation how we are going to do the judgment. So this data here also, actually, if we look at the second slides of chapter 6, these slides I arrange it so that you can understand which data come from which data. Okay, you can trace the calculation from one to the next calculations. So we have a data like this, tensile strength of the paper, and then we have the how we are showing the tendency or the direction of the influence, and then also we have the data, the raw data given like this, and then we have the calculation. The equation is here, and then when we try to do single vector experiment analysis, from the data here you have to convert it into, you have the data, you have to make a further calculation, and you have to fill up the second last column, second last column here, whereby the 60 here is the value of y1 dot, 94 is the value for y2 dot, and we have the average for y1 dot, average for y2 dot, and so on. So then you can see how, what are the equation that we use in the next analysis. And then the same data also is used to explain the analysis of variance, how we calculate the total sum of square, SST, SST treatment, SSE. Okay. And we have another table here. 382.79 is the value of SST, which is SS treatment, not SST. Okay, it's SS treatment sum of square. So you also have the error here, sum of square 130.17, which is actually calculated from this error sum of square. The formula is shown in this slide, and so on. So second slide actually showing another way. It's just another way of showing how the calculation is to be done by using the methods being explained in the first chapter 6 slides. Okay. Now we have an example here. We have data. We have the average. Then we have a data. We have the different level here. We have one factors. We have different level. We have 6 observation for each level. Okay. And then we have to calculate the total for each level. And then we have to calculate the average of each level. And we have the y1 is the average for the first level, y2 is the average for second level, and so on. So from this, we have a problem. Let's see. The question is, hardwood concentration 5% and 20% produce the same paper strength? So this is the equation. So the hypothesis, we have to write it as 0 or null hypothesis mu1 equal to mu4. Okay, 5%, 20%. 5% is the for the level 1, 20% is for the levels 4. So we have to compare this data here. Okay, the data, the first level and the data of the fourth level. So we have the average 10 and average 21.17. From this value only, we can see that the average or the mean is not equal. So that means we can say that the paper strength is not equal. Okay? But it is not enough. In its value is not enough to show that or to do comparisons between level. So we have to do the calculation. This is the formula. T is equal yi minus yj divided by square root 2 MSE divided by n. So we have to calculate. N is a small n. Don't do mistake. Don't mistake with large n. Large n in this case will be 30, but small no 24. Small n is 6. So we have to divide by 6, and then we have the value here is minus 7.58. So we have the n is 6. So note that the MSE is equal to 6.51 calculated during the ANOVA, which is always carried out before the test or in equilibrium means. We have the MSE value 6.51. So from that, we have to determine the degree of freedom. Make sure the calculation is correct. The degree of freedom in this case is not equal to degree of freedom in the previous chapter. You just deduct the number of response by 1 or by 2. No. Because we have a different level, we have 4 different levels to compare. So we have to use this calculation. A is 4, is the level number, and is the response of each level. So we have the value here 20. So decide at type 1 as a level. We use 0.01 as the ANOVA for this example. Find the limit from the T table. So the T table, we have to look on the T 0.0120, which is equal to 3.0. Okay. So we have the T value is minus 7.58, and then we can make conclusion whether it's smaller or greater by using the method, this one here. Okay. Okay. So in this level, in this chapter, you can maybe some of you can realize or might be thinking we are using the two-tail test. Okay, two-tail test. Two-tail test. But why when we look at the table, we are not dividing the alpha with 2? Okay? Just remember in this chapter, when you do the analysis using the ANOVA, do not divide the alpha by 2. Just remember it as shown in the slide. Just remember like that. The alpha we don't have to divide by 2. This is the normal practice in analysis using the ANOVA. And then we have the general procedure to test the individual level means, calculate the T using the equations 6.1, determine the degree of freedom, specify the type 1 error alpha, because we are using the type 1 error alpha. Then we have to look at the plus minus T alpha. Okay, make conclusion by component calculations like just shown in the previous slide. So yeah. So that was the contents, the same contents being explained in second slides. The same content is explained until page 16. Okay, analysis of variance, how we compare between two variants, comparing between level 1 and level 4. This is the explanations that I extracted it from a book. Okay, so next is multiple comparison using the ANOVA. No, sorry. The next is a dual analysis of model accuracy checking. Uh, uh, there is a requirement of error in analysis. Error ij, epsilon ij, result from measurement error and the effect of nonsense factor that are not considered in experiments. EIJ should satisfy the following requirements so that the F0 ratio will follow an F distribution. We have already learned how to read the F alpha, mu, V1 and V2. And we have to compare, or we have to do the judgment by looking at the F alpha, V1, V2, and F0. So the data must be normal distribution, independent distribution, and also we have the zero mean value. We also need to have the constant variance at all runs. This is the requirement of the error epsilon ij. In actual model check, the residual Eij instead of error ij will be checked. The one is E for the residual, the other one is epsilon ij. We refer back on the data given from the previous sample. We have data here. We have the average, we have the total average, and then we have to calculate the epsilon ij, theoretical error. And we have the residual error, which is the estimated error. We can also call it estimated error. The formula is shown in this A1 equation. So we can assume that mu ij is equal to yi. Then we also can assume that epsilon ij is equal to Eij. And look back on this data here. We have data we can calculate the residual by the data here. Okay, using this formula, you need to create another table showing the residuals value. Okay, from this residual value, we have to do the residual analysis. The number of residual is equal to the number of observations. It must be equal because you are calculating on using each data from observations. Okay, and then the normality assumption is checked by plotting the residual estimated error on the normal probability paper. We can do plotting. The independent assumption is checked by plotting the residual estimation error against the time or run order in which the observations were taken. If you notice, you can see here that we have number here minus 3.012, minus 2.04. It's actually the sequence of experiments. 17.1 means that this is the first data taken. Okay, first data taken, the value is 17. Second data taken is, where is it to here? Actually, have to okay. This is the second data taken, and then we have the third data taken 23.3. So we calculate it, we record it, and then we can calculate the residual, and then we can plot a time table. So for the independent assumption is checked by plotting the residual estimated error against the time or run order in which the observation was taken. So we have to plot it using the sequence here number. We have to plot the first data must be 1.33, the second data must be 1.0, the third data must be 1.83. The zero mean assumption is satisfied automatically if the equation A1 is used to calculate the residual. In practice, constant variance is indicated by constant range. So the assumption of equal variance is checked by plotting the residual against the level and comparing the spread of the residual. Range is different between the max and minimum residual in a run. So if you plot the value of the residual, okay, and then you compare between the level, you can see the assumption of the equal variance. We can see we can compare the variance, we can compare the between the different level. So this is to check normal distribution. Okay, we plot it in the type of graph like this. We use this formula, we calculate it, and then we plot all of the data. We have the epsilon k. So we plot like this, and then from the value of k, we have 1, 2, and so on. Okay, rank the residual in ascending order 1, 2, 3, and so on. Estimate the calculations, addition function value for ek, and then we calculate it. Plot n, normal probability paper, if the point cluster to a straight line, the residual distribution is close to normal. So in this case, we can, if we get in a straight line, so we can say that the residual distribution is close to normal. So to plot a graph EK and PK, you have to produce a table. So this is a table. We have the first data until the 24th. We can calculate the EK and also calculate the PK. PK is a cumulative differential function. And we can check the independent distribution. We can plot it like this. If the distribution of the point is random without any sensitivity pattern, the distribution of EIJ is independent. Okay? And then we have to plot it based on the run order. In this example, we have to plot it in sequence started from this data, the first, the second, the third, the fourth. Where is the fourth? Somewhere here we have the fourth, yeah, minus 2.0. And when we plot it in this table, we can see if it's plotted randomly, so we can say that the distribution of EIJ is independent. And check zero mean value. This is the formula. Zero means assumption is satisfied automatically. And check constant variance between a level. We can see the highest, the minimum of each level, the value of each level. We have a minus, less than minus 3, higher than 3, and then we can see the pattern here. So if the range are is identical, the variance is tau constant. Okay, if this one is equal, so we can say that the variance is constant. In this case, it's not so constant. Okay, and then that's some compositions that we can do in chapter 6. But when you look at the slides that I provided today, the sequence of calculation, I think it's much more structured. You can see the formula how we are going to calculate the totals on sum of square, error sum of square, and then we can do a judgment using the f value. And then we have the how we calculate the t, and how can we get the least significant difference for multiple comparison, the LSD, and also we can also see how we are calculating the do experiment or analysis using the multiple comparison using the ANOVA. So the contents in this second chapter, I took it directly from the books. The words used in this slide also is directly taken from the books. I think if there is there are any differences that you could found from these two slides, I suggest you to follow the second slide here. Because the second slide is taken directly from the books and we didn't retype it or we didn't fabricate it ourselves. So the method of calculation comparing between different level also is mentioned in second slides, comparing between the second level and the fourth level, okay, whereby the first the example shown in the first slide was comparing between the first and the second level and the fourth level, and also We have a short example here. Example 2. I provided a question here. Question example 2. Researchers want to test a new anti-anxiety medication. They split participants into three conditions: 0 milligram, 50 milligram, and 100 milligram. So we have three levels. Then ask them to rate their anxiety level on the scale of 1 to 10. Are there any differences between three conditions using alpha 0.05? So from this, you can do the calculation. I will show you the calculation. From a table, you have to create another table, which is the single factor experiment with effective model. We have to create this table. So from this data, you can create, we have the value as shown in this slide. So the method of calculation is shown in the left side, where we can see here we have the MST. MS treatment is 49, MSE is 0.57. We have to put it in this column or in this box here. The SS treatment 98.67, SST is 108, SSE is 10.29, and then you can calculate the F0. Okay, the F0 is equal to MS treatment divided by MSE, and table you are using the alpha 0.05. So degree of freedom 3 minus 1 and 3 times 7 minus 1, you have 0.5, 2, 18. Look on the F, compare it, and then you can do the analysis. So there is another question here. Using this data here, please do calculation by using the previous method shown in this slide. Please do your own calculation using analysis of variance. Okay, calculate the SST, SS treatment, and then do the analysis of variance comparing the F0 and F table, and also please try to compare between level. Okay, such is shown in 6.2.2. You might select either one or either two of it. Okay, you can compare between the level, first level and third level, or maybe you can compare between the first and the third level, or maybe you can compare between the second and third level. It depends on you. You can select two of it, okay, from T. So you can make comparison and then do analysis of variance just as shown in example 2. So as much as you can do, or as much as calculation that you can do it, write it in a piece of paper and save it in PDF file. I want you to submit it in the next class, which is on Thursday. But the next class, I will not conduct any online class. This question here, you can submit it in that day, okay, in Tuesday. you can submit in Thursday. So the question here is orthogonal design of process automation and its application to plasma etching. Okay, describe an experiment to determine the effect of C2F6 flow rate on the uniformity of etch on a silicon wafer used in integrated circuit manufacturing. Three flow rates are used in the experiment, and the resulting uniformity for the 6 applicant follows. So we have a flow rates. We have 125, 160, 200, and each of it we have the 6 sample response. So you can do calculation comparing between this one. Does F2 flow rate affect its uniformity? So you can calculate it using the F0, you can calculate it using the F distribution, and also yeah, just use the alpha 0.05. Okay, in this example here, use the alpha 0.05. Okay, I think that's all for today.